In this lesson we will discuss current flow in a series circuit. Resistors may be connected in a circuit in series or parallel. If the voltage source is connected within the ring or loop containing the resistors, the resistances are connected in series, hence the name series circuit. If the voltage source is placed external to the loop, the result is called a parallel circuit. Let's first discuss current flow in the circuit. There are two important points to consider when discussing current flow in a series circuit. Number one, there is only a single path for current flow. Consequently, a series circuit cannot contain a point where the current may divide and choose another path. Number two, the current has the same value at every point on the circuit. Let's now discuss the individual voltage drops across resistors in a series circuit. The source voltage E in the circuit shown is defined as the total electromotive force available to drive the current I around the series circuit. A portion of this EMF will be used in overcoming the resistance of R1, another portion for overcoming the resistance of R2, and the remainder will be responsible for driving the current through R3. Let us assume the voltage drop across R1 is V1, the voltage drop across R2 is V2, and that across R3 is V3. Thus the equation is E equals V1 plus V2 plus V3. In determining the total equivalent resistance of a series circuit, we refer to the already established relationship E equals V1 plus V2 plus V3. Ohm's law states that the voltage V across the resistor is equal to the current I through the resistor multiplied by the resistance R of the resistor, or V equals IR. Therefore, V1 equals I R1, V2 equals I R2, and V3 equals I R3. By substitution we get E equals IR1 plus I R2 plus I R3. Factoring out I gives us E equals I times the sum of R1 plus R2 and R3 as shown. The total equivalent resistance in a series circuit is equal to the sum of the individual resistances R1 plus R2 plus R3 and can be expressed as R sub T. What is the total equivalent resistance in the circuit shown? The total equivalent resistance R sub T is equal to 10 ohms plus 15 ohms plus 20 ohms, or 45. The current in the circuit I is equal to the voltage divided by the resistance, or 20 divided by 45, and equals 0.44 amps. What is the voltage drop across each of the resistors? Voltage drop V1 across the 10 ohm resistor is equal to the current times the resistance of 10 ohms, or 0.44 times 10 equals 4.4 volts. Voltage drop V2 across the 15 ohm resistor is equal to the current times resistance of 15 ohms, or 0.44 times 15 equal 6.6 volts. Voltage drop V3 across the 20 ohm resistor equals the current 0.44 times the resistance of 20 ohms, or 8.8 volts.